So in topology, we have a lot more invariance than we have constructions. And usually to completely classify some topological setup, you need both invariance to distinguish between different objects, to tell you that things you hope are different really are different, and you need constructions to show when they are equivalent, that they are equivalent. And there are a lot more invariants than there are constructions. The most recent construction is Ricci flow, which is in fact a construction in metric geometry, but it's turning out to have very important applications both in topology and more recently in algebraic geometry. So I want to tell you a little bit about one of those applications today. I thought I would start with the simplest case of Riemann surfaces, where the theorems that one can use Ricci flow to establish, in fact, were known over 100 years ago. But still, Ricci flow gives another way to think about these theorems, uniformization of surfaces. Anyway, as a warm-up, I'm going to talk about the case of surfaces. Then I'll talk a little bit about the underlying geometry behind the Ricci flow, talk about Riemannian curvature and Ricci curvature. And then I'll talk some about the equation and some of its basic properties. And then I'll talk about the applications in the hands of Perlman, one of your natives, to the topology of three-dimensional manifolds. So let's start with a closed-oriented surface, sigma. And I'm interested in studying the topology and eventually the geometry on this surface. So I'll impose a Riemannian metric. So this is something you can do on any surface and in fact on any manifold of any dimension. There's always a nice Riemannian metric. You construct it locally. You cover the manifold by coordinate charts. In each coordinate chart, it's a Euclidean coordinate chart. Use the Euclidean metric and then paste them together using a partition of unity. But in fact, there's a huge space of Riemannian metrics, a huge infinite dimensional space, and one often searches for good metrics. So that's Ricci flow is in fact an attempt or a method to find a good metric. And I'll say a little bit more as I go along, even in the case of surfaces, what we mean by this. So I'm going to follow a path which is fairly close to the classical path for these surfaces. The Riemannian metric gives us, of course, on each tangent plane, so we have the Riemann surface, and every tangent plane now has a metric or a positive definite inner product, so it's identified with the Euclidean plane, R2, and in particular, this Riemannian metric gives us the analog of multiplication by I, a complex structure. It turns this plane into a plane isomorphic to C. So we have J, which is an endomorphism of the tangent bundle of the Riemann surface, and it's like multiplication by I, its square is -1. That's called an almost complex structure. It's a complex structure on the tangent bundle. Now the magic thing in one complex variable or in two real variables is this almost complex structure in fact can be integrated. So there is an underlying complex structure. On sigma, completely determined by this Riemannian metric. If we put a different Riemannian metric, we might well get an inequivalent complex structure, but we have a complex structure on sigma. That is to say, they're local holomorphic coordinates, so around every point in sigma, there's a neighborhood and an isomorphism to an open subset in C, so that the almost complex structure restricted to U is given by the usual multiplication on the tangent spaces to C. And then automatically, as you pass from one of these coordinate patches to another, the overlap functions are holomorphic. Okay? So sigma becomes a complex curve, complex one-dimensional manifold. Okay? Now that's really a magical step. This is something you can do in real dimension 2, complex dimension 1. In higher dimensions, just because you have a J, an almost complex structure, there's no reason to believe you can integrate it. That's a very difficult and complicated problem. But here, we always have a complex structure. Okay? Now, let's invoke another classical theorem about complex structures. If we consider the universal cover of sigma, this is a simply connected complex surface now. Simply connected because it's the universal cover. Complex curve, I should say. And there's a classification of these. There are three possibilities. This simply connected complex curve is either isomorphic to S2, C, or the open unit disk inside C. Okay? And the fundamental group of sigma acts as complex, well, as holomorphic transformations on the universal cover, acts freely with quotient the original surface. So this surface is now written as the quotient of S2, C, or the unit disk inside C with their induced complex structures by a group of holomorphic automorphisms acting freely. So if our surface was oriented, in this case, there's only one possibility. Sigma is, in fact, biholomorphic to the two-sphere. In this case, again, since we took the manifold to be orientable, in fact, sigma is the quotient of C by a lattice, free abelian group of rank 2, discretely embedded in C. So it's some torus, 2 torus. And in this case, well, the unit disk, or the upper half plane, has a metric, the Poincare metric, that's invariant under the full group of complex symmetries. So sigma is, let's say, the quotient of the upper half plane, which is another way to think of the unit disk, by some group of symmetries, and this group automatically preserves the Poincare metric, which is a metric of constant curvature minus 1. Okay. So we found now, through this mechanism, we imposed a Riemannian metric. We used it to get an almost complex structure, which we could integrate to get a complex structure. We took the universal cover. That's a simply connected complex curve. It has to be one of these. And then we see the surface is given as one of these 3 standard complex curves, modulo a group of symmetries, preserving a natural metric. Here it's the flat metric, here it's the round metric, and here it's the constant curvature minus 1 metric. So in fact, there's a nicer metric. So the nice metric is the constant curvature metric. Okay. And this is one of the ways to get what's called uniformization for Riemann surfaces. And out of that, you can completely classify all Riemann surfaces, though there are other ways to do it. These closed-oriented ones are either the two-sphere, topologically a torus, or and now you have to figure out what all these groups gamma look like. These are the surfaces of higher genus. Okay. Well, there's another way to think about all of this, another way to produce this end result. consider the following partial differential equation for metrics on a Riemann surface. So I'm going to think about a one-parameter family of metrics. So it's a family of metrics parameterized by t, and I'm going to write down a differential equation. It's a parabolic equation for how this metric changes with time, and the answer is take twice the Gaussian curvature of the metric, which is a function on the surface, depending on t, times the metric. Okay. So this is a differential equation for varying the metric. You start with any g0, and you try to solve this differential equation. This is the Gaussian curvature of sigma with the metric gt. Okay. Well, we now know what happens. One of three things happens. There are three possibilities. Number one is the equation. So first of all, there's an existence and uniqueness theorem. Given an initial metric, you can always solve this equation and solve it uniquely up to some maximal time, which might be finite or infinite. A priori, you don't know. So the equation. So one possibility is the equation develops a singularity at finite time. Let's say t. And I'll give you an example of that in a minute. Second possibility is, well, the equation exists for all t less than infinity. Okay? And sigma gt converges to a flat metric on sigma as t goes to infinity. And the last possibility is the solution exists. I should say solution instead of equation. The solution exists for all time, and renormalizing by 1 over time converges to a hyperbolic metric on sigma. Okay. Let me go on and say a little bit more about the first case when there's a finite time solution. So in case 1, the diameter of sigma gt goes to 0 as t approaches this limiting time. So the manifold is shrinking to a point, and if you rescale by the time to blow up, gt, this converges to a round metric. Okay. Well, there we have it. These three possibilities are these three possibilities. If the solution develops a singularity in finite time, as the singularity develops, the manifold is shrinking to a point, and if you scale it back up appropriately, it's becoming rounder and rounder. It's converging to the round metric on the two-sphere, and you've constructed this isomorphism. If you're in case 2, the solution exists for all time, and you're converging to a flat metric, of course, you're producing this picture. And in the last one, we're producing the hyperbolic metric or the Poincare metric. Okay. Again, we have to rescale by 1 over time. Did I do that right? Yeah. Okay. Now let me just point out, this equation deforms the metric through preserving its conformal class. Because the equation of the form, the derivative of g with respect to time is simply a functional multiple of g, you're preserving the conformal structure. So as this argument preserves the conformal structure, this one does too. So this produces for you the correct, nice metric in the conformal class of g, the metric that you started with, g0, just as this argument did. Okay. Now this was not the original proof of uniformization, far from it. It was only understood in the last 10 or 15 years that it works this way for surfaces. Okay. So now I want to talk.
What do you mean by saying it's recent? The equation, the idea to consider the equation itself, or the proofs of all the statements? What is?
Yeah. So the equation.
What is the history of?
Yeah. So the equation was first introduced in, I believe, 1982.
Even in dimension 2?
Yes.
Really? Oh.
Yes.
Okay.
By Hamilton in mathematics, and independently by, oh, the name's going to escape me in a senior moment, Dan Friedan in physics.
Even in 2 dimensions, it was
No.
not known before 1982.
I don't think anybody had ever written this equation down at all. Yeah.
It's not a curvature.
Okay. No, it's not, but it's like a heat equation.
No.
Yeah, this is, I mean, it's very closely related to the heat equation, but it's a nonlinear tensor version of the heat equation.
Like, normally you just optimize the heat equation to prove the...
Right.
And I think those people, they were smart people, those who invented it, Osgood and Kirby and Riemann. Yeah, so yeah, well...
Yeah, I don't know. As far as I'm aware, this equation had not been...
You know there is a very recent book on history of the Riemann uniformization theorem by Etienne Gis.
Ah, no, I haven't seen it.
It's like a year...
I should look at that, yeah.
So,
I should say this, I've written the equation in dimension 2 where it simplifies. The equation that Hamilton and Friedan wrote down was the equation in all dimensions where you don't use Gaussian curvature, you use Ricci curvatures, we'll see. And I've just simplified it in this case of 2 dimensions. All right. So let me talk a little bit now about when we go to higher dimensions, when we're trying to write down an analogous equation, we have to figure out what replaces Gaussian curvature. And of course, we know in higher dimensions, the full generalization of Gaussian curvature is the Riemann curvature tensor. So let me talk just a minute about that. This turns out not to be the appropriate thing to put on the right-hand side of the equation. We have to have a related curvature, but I'll come to that after I've talked a little bit about Riemannian curvature. So let me start with parallel translation. Do we have any colored chalk? Yeah. So suppose I have a smooth manifold, and I have a vector field, smooth vector field on the manifold, and I have a curve, gamma of t. And then I have these tangent vectors, tau of t, which is in the tangent space to the manifold at gamma of t. And let's imagine, for this example, that the manifold is actually embedded isometrically in Euclidean space. So I have a metric on the manifold which is induced from its embedding in Euclidean space. I want to define the parallel translation of the vectors along this curve, these tangent vectors, back to tangent vectors in the base point, in the tangent space of the base point, gamma of 0. So I want to do parallel translation along gamma, but moving back to the origin of tau of t. And this is going to be some 1-parameter family sigma of t in a fixed tangent space. Okay. And the way I do that is I simply take parallel translation in Euclidean space, just the ordinary parallel translation back. But of course, if I start with a tangent vector to the manifold and I just translate it in Euclidean space back, I won't get a tangent vector. So you then perpendicularly project onto the tangent space. So you parallel translate in Rn, and then project perpendicularly, orthogonally, onto the tangent space to the manifold. Okay. So that turns this family of tangent vectors along the curve into a family of tangent vectors at the initial point, and then I could differentiate that family, take d by dt sigma of t at t equals 0, and that will be what's called the covariant derivative in the direction of this curve of this family of tangent vectors, tau. So this notion of parallel translation allows me to differentiate families of curves, families of vectors, vector fields, along curves or along other vector fields. Okay. See, I can't differentiate naively anyway this original family of vectors along the curve because they lie in different vector spaces. I need them all in the same vector space before I can differentiate them. So this notion of parallel translation, which exists not only for manifolds embedded in Euclidean space, but quite generally, as long as you have a metric on the manifold, you can define a parallel translation, a covariant derivative, leads to this differential operator. And let me write down its formal properties for you. So I've presented it as differentiating a vector field along a curve, but in fact, you can see the answer only depends on the tangent vector to the curve at the initial point. So you can view this operation as a pairing given two vector fields, x and y are vector fields. This is a new vector field, which is called the covariant derivative of the vector field y in the x direction. And the basic properties that it has, so this is dependent on the existence of a metric in the manifold. So the basic properties are it's linear over the functions in the first variable. That is to say, if you multiply the vector field x by a function, you simply, and then differentiate, you get the same thing as if you differentiate using x and then multiply by the function. It's a derivation in the second, over the functions in the second variable. So you get the similar term, the linearity over the function, but then you get the vector field applied to the function times y. So that's a derivation property over the functions in the second variable. It's a metric connection, which says that the derivative of the inner product of two vector fields is simply given by this derivation rule. Okay.
And by placing x in front of function, you mean differentiation, right?
That's right. So x is a vector field. By definition, it's a derivation on the functions. Okay. And the last property, which is a very mysterious one. I'm not a geometer, so I don't really understand this property. But it's the torsion-free condition. It's a symmetry condition between the interchanging the two the position of the two variables. It's the bracket of x and y. So this is a so-called Levi-Civita or torsion-free condition. It turns out, you see, these conditions are completely general. They have nothing to do with the metric. They only use the underlying smooth structure in the manifold. This condition ties the covariant differentiation to the metric. So the metric here is written using the brackets. I haven't explicitly written it down, but that's where it enters these equations. And the theorem is there exists a unique covariant derivative given a metric, satisfying these four properties. Okay? So I gave you a hint of a geometric definition over here. This is the more formal algebraic properties. These characterize it. It's easy to see when you unravel this definition that it has all of those properties. Okay? Okay. So that's covariant differentiation. The Riemannian curvature is a measure of the failure of second derivatives to commute. So you now define a tensor that, well, you define an object that depends on two vector fields. It's simply the commutator of the two second derivatives, the two second covariant derivatives, and then there's an extra term in case they don't commute. Usually we work in a local coordinate system, and x and y will be, for example, partial derivatives in the coordinate directions, and then this term will vanish. But in general, you have to have it here. So a little lemma. So what is this? This is a map, R of x, y, takes vector fields to vector fields. So if you have a vector field z and you apply all these covariant derivatives to z, you will get another vector field. So this operation takes vector fields to vector fields. It turns out that, well, let's write down the full 4 tensor. Let's consider this operation. So apply x and y to a vector field, rxy to a vector field z, you get another vector field z prime, and take the inner product of that using the metric with w, and that's called rxy wz. And the lemma says this is tensorial in all 4 indices. So if you multiply any one of these variables by a function, that function pulls out. So it has the same property, linearity over the functions in all 4 variables, which means it's a 4 tensor. Secondly, clearly from the definition, it's skew in x and y. Because of the fact that we're working with a metric, it's also skew in z and w. And lastly, this torsion-free property, this property tells us that it's symmetric in interchange of x, y, and z, wz. So this is a 4 tensor. It is an element in this, it's a symmetric polynomial of degree 2 on the second exterior power of the tangent bundle. And you often write it as Rijkl dxi wedge dxj. That's skew symmetry in these 2 variables. Tensor dxk wedge dxl. Skew symmetry in the last 2 variables, and this is a symmetric tensor. Okay. That's the full Riemannian curvature tensor. It generalizes the Gauss curvature in the following way. If you take any pair of orthonormal vectors, x and y, so x and y are orthonormal at a point, and you consider r xy xy, you'll get a number, and that number is the Gaussian curvature in this 2-plane direction of a surface in the 4-manifold. So it's a collection, among other things, it's a collection of all the Gaussian curvatures in all the directions, 2-plane directions in the manifold. And they fit together.
Does Jacobi identity follow from this whole? I mean,
yes, everything follows from these definitions. Yeah.
No. I mean, you have 4 properties on the left.
Yeah. No. The Jacobi is another one. Yeah.
It's not a complete loop.
No. Okay. So this is one way in which Gaussian curvature can be generalized, but it's not appropriate for this differential equation, as you can see just by, as a physicist would say, by looking at indices. So if I work in local coordinates, the metric is a symmetric 2 tensor. It has 2 indices, I and j. And I can ask, well, can I put some sort of Riemannian curvature here? But this is something with 4 indices. So this has the wrong tensorial structure to be an appropriate equation. So this makes no sense. And if you think about it, what's important here is that the Gaussian curvature of a surface is related to area. There's a beautiful formula for Gaussian curvature. The Gaussian curvature at a point compares the area of the ball of radius r around that point to pi r squared, the area in the plane. That difference, area in the plane minus this area divided by pi r to the fourth and multiplied by 12, the limit as r goes to 0 is the Gaussian curvature. So it's a measure of the area discrepancy in this surface from the Euclidean area growth. So the Riemannian curvature tensor is a measure of those area discrepancies in all two-plane directions. But what we really need is something that measures the full area of the n-dimensional ball, not the areas of all the two planes, the areas in all the two-plane directions. Well, that curvature is known, has been known a long time. That's the Ricci curvature. And the Ricci curvature is defined this way. So it's a symmetric two-tensor. Ricci ij is formed by tracing over an orthonormal basis in two of the coordinates. Okay, so it's a trace on two of the four indices of the Riemannian curvature. It's a symmetric two-tensor, so it has the right structure to fit on the right-hand side of the equation. And there's a beautiful formula that shows how Ricci curvature is related to volume, the full n-dimensional volume. Let's see, I've written it down somewhere, yes. If you look at the volume of the metric in Gaussian coordinates around a point, it's written as 1 minus 1/6 Rij xij plus xi xj plus order x cubed. So to leading order, the volume out times the Euclidean volume element. Okay. So Ricci curvature is a measure of the discrepancy to second order between your volume element in the manifold and Euclidean volume. Okay. So it turns out this is the right thing to put on the other side of the equation. And we write the Ricci flow equation, dg dt is minus twice Ricci curvature of g of t. If you write it in local coordinates, this is a symmetric two-tensor depending on time and the point, and it's minus twice the Ricci tensor of the metric g of t at that point. Okay. Now there are other ways to think about this and see that this is a reasonable equation. Let me just write down one of them. You see the Ricci curvature in Gaussian coordinates, the Ricci curvature looks like minus a half the Laplacian of the metric plus lower order terms. So if I plug that in here, I'll see that dg dt looks like the Laplacian of g plus lower order terms. So this is a heat equation with lower order term corrections, but it's a heat equation for tensors, not for scalars, like say, the heat equation for temperature. So this also should convince you.
This holds in normal coordinates at one point.
Yes, this is this computation at one point, right?
So once you change the measure, you have to change the coordinates.
Yes, yes.
It's not that easy.
That's right. But this indicates, for example, that the minus sign here is a good thing, right? So this is the Ricci flow equation.
So the equation in parentheses, in the block, it is a tensorial equation.
Okay.
It is. Okay.
No. It's one point. It's at one point.
Yeah, and this is a computation at in Gaussian coordinates centered at a point. All right, so let me say a little bit about this equation. First of all, this is a geometric equation. That is to say, well, there are two ways to think about it. One, it's independent of the coordinates we use to write it down, or it's invariant under the action of the diffeomorphism group. Okay. But modulo this large gauge action, it's a so modulo this, it is a strictly parabolic equation. So if you take an appropriate slice to the action of the diffeomorphisms as you can, and you write this equation restricted to the slice, it's a strictly parabolic equation. And so you see that, in fact, we have short time existence and uniqueness. That is to say, there's some capital T, finite or infinite, but certainly positive, and a solution. So for an initial metric, G naught given, a solution G of T defined from 0 up to, but not including this time. G of 0 is the initial metric. And all other solutions are subsolutions of this. Okay. As we saw in the case of Riemann surfaces, for example, if you start on the topological, on a smooth manifold, the Riemannian manifold, the topology of the two-sphere, this will be a finite time solution. The solution will develop singularities in finite time. In the other two cases, the torus and the hyperbolic case, the solution will exist for all finite time, all the way up to infinity. Okay. So this is completely general in all dimensions. Let me just show you some solutions to this equation in the simple cases where we can, a couple of simple cases where we can actually, or one simple case where we can solve it. If you start with an Einstein manifold, this simply means that the Ricci curvature of the metric is some multiple of the metric. Yeah, that's what Einstein means. It's the real Einstein case. Then, in fact, you can solve this equation explicitly. G of t is 1 minus 2 lambda t times G naught. Turns out, so you see I'm scaling the metric by a constant conformal factor depending on time. When I do that, the Ricci curvature doesn't change, and you see, if you differentiate this equation, you see dg dt is minus 2 lambda g naught, which is minus 2 Ricci of g naught. But because of this conformal change, that's also minus 2 Ricci of g of t. So that solves the equation. It's the unique solution. And you see whether or not the solution is going to exist all the way to infinity or have a finite time singularity simply depends on the sign of the Einstein constant. If it's positive, this thing becomes singular at 1 over 2 lambda. If lambda is 0 or negative, the solution exists for all time, mimicking what we saw in the case of surfaces. Positive Ricci constant is the two-sphere. 0 Ricci constant would be the flat manifold, and negative Ricci constant would be the hyperbolic. So flat and hyperbolic, the flow exists for all time. In the positive case, it becomes singular in finite time. So this works for Einstein manifolds in all dimensions. If you have a positive Einstein manifold like the round end sphere, it will become singular. It will, under Ricci flow, it simply scales down conformally. It becomes singular at this time 1 over 2 lambda when it's completely shrunk to a point. So this would be the end sphere with the round metric. If we start with a hyperbolic manifold of any dimension, I've done it for a surface, but you could do this, a hyperbolic manifold of any dimension n. In fact, under this flow, it simply inflates by a larger and larger constant factor as time goes on. So at each time, this is a constant factor inflating the metric up. The surface becomes of larger and larger diameter. Diameter goes to infinity. Area, volume goes to infinity. Curvature goes to 0. But it's always conformal to your original hyperbolic surface. And if you were to rescale by 1 over t, you would come back to, well, you would converge to 2 lambda times the original metric. So that's exactly what I did in the case of a hyperbolic surface. I rescaled the metric by 1 over t. That's the appropriate rescaling in this example as well. And if you started with a Ricci flat, then the flow would be the constant flow. Nothing would happen. Okay. Well, those are a few cases where we can actually solve the equation explicitly. That's about it. In general, it's very hard to say what this equation does. There are some techniques. One should be suggested here, or rather here. Where did I write it? Here. Well, here. The maximum principle. That's an important analytic technique that helps you control geometric quantities. There are some computations you can do, explicit computations that help you control certain quantities. But in general, you have great difficulty in understanding what this equation does. Perlman's great breakthrough was to be able to control the region for three-dimensional flows, to control the regions where singularities are developing, regions where the curvature was sufficiently high. He was able to give qualitative, topological, and geometric control, and that was enough to allow him to prove the various topological consequences. But the idea here is a very simple one. The idea is that...
Before you erase, did anyone consider some scalar curvature flow? All that motivation are the same, and that would be conformal by definition. And there's some fourth order equations involving scalar curvature, but they're fourth order, so progress is very difficult. No, I mean just put
R times G
times metric instead of Ricci.
Okay, so
that would be the same in normal coordinates actually.
So one variant of the Ricci flow equation you do consider is minus Ricci plus a constant, depending on time, times G. And these equations turn out simply, I'm forgetting now, maybe I need this to be a constant independent of t, I'm not sure. But these equations turn out to simply be a rescaling of time from the original equation.
I mean scalar curvature.
Yeah, sorry, that's what I should have.
Just a number, not to 10, yeah?
But that's not, yeah, sorry, I should have written.
You generalize Gauss, you can generalize Gaussian curvature in different ways, right?
Right.
One way you get a Ricci tensor, which you can subtract from the original. Another thing is, yes.
Right, that's what I want to do.
That's what I mean.
Yeah. This one turns out not to have a maximum principle.
Despite the same expression.
Yeah, yeah. There's no maximum principle here.
So it's a trick that you wrote down this local coordinate expression.
Well, I mean, I don't need this local coordinate expression. I was using that as motivation only. You have to prove the maximum principle for the Ricci curvature, right? And that argument doesn't work more generally. Okay. So I was trying to motivate a little bit what one believes this flow ought to do quite generally, which is, like the heat equation, you expect this flow to smooth things out, make the metric on the manifold much smoother, and hopefully, if you're lucky, completely homogeneous. So that's what happened in the surface case. All the bumps in the manifold are smoothed out. If you think about a Riemannian surface, so here's positive Gaussian curvature, and here's some negative Gaussian curvature. What's going to happen is, because the flow is the derivative of the metric is minus the Gaussian curvature times the metric, these bumps are being brought down or shrunk, and these pieces are pushed out. And in fact, the metric is smoothing out over the manifold, and the theorems that I stated say eventually, either at the blow-up time or at infinity, the metric has become completely homogeneous. So the idea is that in dimension 3, or in fact in all dimensions, the flow should smooth out the metric, make it look the same everywhere, or in other words, make it homogeneous. That's the hope, idea or hope. And that is exactly what happens in dimension 2, and in a weak form, partially what happens in dimension 3. Nothing is known for higher dimensional manifolds along these lines at all. Okay? So maybe I should just say a word about homogeneous manifolds, and then I'll say what Perlman was actually able to show in dimension 3. So we say a manifold M is homogeneous. So this is a Riemannian manifold if its group of isometries acts transitively on the manifold. Okay? So all points look the same Riemannianly. You can't tell where you are on the manifold by making measurements. Well, if G is the isometry group of M, we can define a map from G to M, which sends a group element to the image of some base point x0 under the group element, and this will give us an isomorphism from G mod H to the manifold, where H is the stabilizer of this point x0 inside G. So if you have a homogeneous manifold, it's in fact isomorphic to G mod H, and the metric here is some metric determined on the tangent space to G, some H invariant metric. So in the case of Riemann surfaces, the homogeneous ones are the two-sphere, R2, and the hyperbolic plane. The two-sphere is SO3 mod SO2. The plane is the Euclidean group mod SO2. And hyperbolic space is PSL2R divided by SO2. So those are the three homogeneous manifolds in dimension 2. Now our manifolds, our compact surface, isn't homogeneous. It's not one of these. It's a quotient by a discrete group of isometries of one of these. So locally homogeneous manifolds are by definition manifolds whose universal cover is homogeneous. So their universal cover is G mod H, and they look like, or gamma inside G is a discrete group. Discrete group, and it has to be disjoint from H, except at the identity, in order to have a free action. So this is what all our surfaces look like. The two-sphere is SO3 divided by SO2 mod the trivial group. The tori are the Euclidean group in dimension 3 mod SO2, that's the plane divided out by a lattice. And these are PSL2 mod SO2 divided out by the fundamental group of a surface of higher genus, acting as a discrete group inside PSL2R. Okay. Well, one has homogeneous manifolds in all dimensions, constructed in exactly the same way. You look through the Lie groups, compact subgroups, and then discrete groups inside there. Okay. And one might hope that Ricci flow will take any metric on a manifold and push it to a homogeneous metric. Well, okay. Unfortunately, not all 3 manifolds, compact 3 manifolds, have locally homogeneous metrics. Okay, there are 2 elementary and obvious topological conditions that have to be satisfied if the manifold has a locally homogeneous metric. The first comes from the notion of connected sum. If you have 2 closed manifolds of the same dimension, xn and yn, you form their connected sum by embedding a ball in each of x and y, removing the interiors of the ball, and sewing together a tube Sn-1 cross I, and smoothing it out near the corners so you get a smooth manifold. And this is called X connected sum Y. So this connected sum manifolds have an interesting, well, if these are 3 manifolds, they have an interesting 2-sphere right in the middle that separates into 2 pieces. And if you look at the universal cover of this manifold, it turns out this 2-sphere can't bound a 3-ball up in the universal cover. So it's a homotopically non-trivial 2-sphere in the universal cover, and that's just impossible for homogeneous manifolds with one exception. So a connected sum of 3 manifolds does not have a locally homogeneous metric. For this simple topological reason, this 2-sphere here prevents it. And there's a similar operation using 2 tori. Slightly more complicated to establish, but by a purely topological argument, you can show, for example, if you take, let's take a hyperbolic 3 manifold, non-compact but a finite volume. So this is a hyperbolic 3 manifold, X3, with one end. So the end of this manifold looks like a 2 torus topologically cross an interval that's decaying exponentially fast. Let's take another hyperbolic, finite volume hyperbolic manifold, Y3, again with one cusp, 2 torus exponentially decaying this way. Let's simply cut off the 2 tori, some compact place, X naught and Y naught, and then glue the 2 tori together topologically. That makes a 3 manifold, M3, and you can show that fairly easily this manifold has no locally homogeneous geometry. Okay? So those are 2 fairly simple topological obstructions. This obstruction based on 2 tori, this obstruction based on 2 spheres. Over here, this connected sum operation is fairly well understood topologically. Every 3 manifold can be broken into a finite number of pieces under connected sum, that is, breaking apart pieces like this, into pieces that can't be further decomposed non-trivially. Those are called prime pieces, prime 3 manifolds. Okay. So the theory of 3 manifolds is like the theory of the natural numbers. There's an infinite number of primes, and every 3 manifold, closed 3 manifold, is a product of primes, finite number of primes, unique up to order. The 1 in this structure is the 3 sphere. That acts the trivial under the connected sum, which is the multiplication. So that's what 3-manifold theory looks like. You just have to understand the prime 3 manifolds, and then you understand all 3 manifolds. This operation is a little different. So Thurston actually the same year, 1982, that Ricci flow was introduced, made a general conjecture that if M3 is prime, so can't be decomposed this way under connected sum, then there is a finite disjoint union of tori in the manifold such that the complement of these tori, each connected component, has a locally homogeneous metric of finite volume. Okay? So up to this operation, you can always find, which you may have to do many times, you can always cut the manifold, this prime manifold, open into pieces, each piece of which looks like maybe a hyperbolic 3 manifold, or there are a few other cases in dimension 3 that I won't list. Okay, so that's the geometrization conjecture. It implies the Poincare conjecture quite easily. These tori turn out, as part of this statement, the fundamental group of each torus mapping into the fundamental group of the manifold is injective. These are called incompressible tori. So if the 3 manifold was a homotopy sphere, its fundamental group is trivial, so it has no tori. Therefore, this decomposition is the trivial decomposition. The manifold itself has a locally homogeneous metric, and that means if it's homotopy equivalent to the 3 sphere and it has local homogeneous metric, it is the 3 sphere. So the trivial consequence of this is it's the Poincare conjecture. But this is a...
By the way, when you cut along the torus,
Yes.
you don't require that it's 2 different components, right?
No.
You allow
That's right.
loop graph matrix.
That's right.
and all that.
That's right. That's right. And if you press me, you also have to allow Klein bottles here, but I didn't want to talk about that. All right. So this is a hint that Ricci flow might actually be able to do something in dimension 3. There is this cutting process you have to go through, but in the end, you're trying to get homogeneous metrics. And that's the kind of thing one hopes Ricci flow will produce in general and does produce for surfaces. And this is exactly what Perlman proved. Ricci flow produces the geometric decomposition conjectured by Thurston. And let me just say a few words about what happens. So first of all, you can't just use Ricci flow. Ricci flow, so start with an arbitrary closed 3 manifold, put on an arbitrary Riemannian metric, and apply Ricci flow. The flow will become singular in finite time, almost assuredly. Certainly if you have an interesting topology, like a non-trivial connected sum, it will have to become singular in finite time. Perlman was able to control the nature of the singularities, and they come in 3 classes. So as a singularity is developing, it's either a long, thin neck based on a very tightly positively curved 2 sphere, a long, thin neck based on a very tight 2 sphere with a positively curved 3 ball on one end, or it's the 3 sphere itself. So finite time singularities go with positive curvature. That positive curvature might be in dimension 3, in which case this whole component's disappearing at the singularity. It might be positive curvature in dimension 2, in which case this guy is getting squeezed. Okay. So you imagine the singularity looking something like this. And here we get some sort of degenerate, this is called a neck pinch. We call this a degenerate neck pinch. And here Just as in the constant curvature case, it shrinks to a point. So those are the singularities in finite time. You go in and you do surgery. In this case, you simply cut away this part and stick in a nice standard ball. In this case, you cut away this side and again stick in the ball. In this case, you simply throw it away. You see, we know what these pieces are. They have homogeneous metrics. The metrics becoming round as the manifold shrinks to a point. So these are round manifolds, S3 mod a finite group. So we cut away these singularities, and then we restart the Ricci flow at what was before the singular time. We have a new manifold now. We flow again until we hit another singularity. We do the same process. We continue all the way to infinity, making a Ricci flow with surgery. And it's defined G of t. Now the manifold also depends on time, and it's defined all the way to infinity. And the manifold does undergo changes, and the changes are both topological changes and geometric changes. For example, we throw away certain components, but we're throwing away components that we know have round metrics, and we're cutting out certain regions, and we have to understand what those do topologically. Well, here we have a cylinder, S2 cross I, and we're simply cutting out the middle and sticking into 3 balls. Well, that's the reverse of this connected sum operation. So this does the connected sum decomposition. It cuts open the connected sum pieces. So at finite time, what we're doing, we're throwing away some components we completely understand and like, and we're doing the inverse of connected sum. We're doing the connected sum decomposition. By the time we get to infinity, the manifold splits into 2 pieces. No, that's not what I want to do. Manifold splits into 2 pieces. The part of the manifold where the volume is not collapsing, and the part of the manifold where the volume is collapsing. So, as t goes to infinity, in this Ricci flow with surgery, we write the manifold as the union of a plus part and a minus part along 2 tori. Okay. So MT plus has volume that's not collapsing locally under the metric 1 over t gt, and MT minus has volume that is collapsing locally under the same metric. This is a little reminiscent, we have the trichotomy replicated here that we saw in the case of Riemann surfaces. In the case of Riemann surfaces, we might have gotten a 2-sphere here and it would have disappeared. There are none of these cases. So if you saw this singularity, that was case 1 for Riemann surfaces. This is the hyperbolic case for Riemann surfaces. The volume is not collapsing under 1 over t gt. That's going to the hyperbolic metric. And here the volume is collapsing because it was a fixed size torus, and when I divide by 1 over t, I'm shrinking it down to 0. Okay. Anyway, the manifold decomposes along 2 tori whose fundamental group injects, into the region where the volume is staying locally non-collapsed, so balls of some fixed radius r don't have too small a volume, and then over here, these tori are very long, and then over here it's some collapsed manifold. These pieces, 1 over t gt, restricted to the plus part of t, is converging to a hyperbolic metric, to the 3-dimensional hyperbolic metric. The collapsed stuff, we don't understand the metric here through Ricci flow, but because it's collapsing to lower dimensional things, which are fairly easy to understand using the theory of Alexandrov spaces, I have to mention that here, these pieces are understood topologically and in particular have locally homogeneous metrics. You don't necessarily, as far as we know, get the metric from Ricci flow in any natural way. That happens over here, but we do get enough of control because of this collapsing to understand the topology. Once we understand the topology, we can just see that these manifolds are all in the list of manifolds with locally homogeneous metrics. They look like circle bundles over Riemann surfaces or two torus bundles over the circle. That's what they look like. So that completes the proof, and you see Ricci flow in dimension 3 doing a lot of what it did in dimension 2, but working with these topological complexities. It has to do these connected sum decomposition because otherwise there is no homogeneous metric. It has to do these torus decompositions because otherwise there is no homogeneous metric. It does all of that, and at least on the hyperbolic pieces produces the hyperbolic metric, and in the other pieces tells you what the topology looks like. Okay, I'll stop here. Thank you.
Question?
Yeah. So, can you say one word about entropy, which was perhaps introduced by Riemann?
I'm sorry.
Entropy.
Entropy. Yeah, so if you look at Perlman's first paper, the first 6 sections of it deal with this functional W, which he calls entropy. And he uses that to show, for example, that Ricci flow looks to some extent like a gradient flow. So he proved no recurrence up to rescaling. What he actually needs to prove all of this, entropy is not, as far as we know, a good enough function to make this analysis because you don't understand how entropy behaves under surgery. So he actually goes in and introduces a local version of entropy, which, as far as I'm concerned, is the most original contribution in all of his work. I could say a word about it. Yeah, okay. It somehow, I think, should produce a parabolic version of the Bishop-Gromov inequality relating volume and Ricci curvature. There should be some parabolic version of that. But anyway, here's what he studies. He fixes, so we're not going to think of Ricci flow in space-time, but this isn't Einsteinian space-time. This is really a product. We have time, and then we have our fixed manifold. So it's M cross the time interval, AB. Okay. We fix a point at the top, x naught, t naught, and we're going to define a function at earlier times, y and t. And we consider paths, gamma of t, gamma of tau, let's say, parameterized by backward time. So that means gamma of tau is in the time slice m cross t naught minus tau. And tau here runs from 0 up to t naught minus t. Okay? These paths always start at x naught, t naught, and y and t can vary. In fact, we'll usually think of t as fixed and y varying. Okay. He then defines what he calls the L length, which is a strange integral. Integral from 0 to, let's call this tau naught, square root of tau, scalar curvature at gamma of tau, plus the square of the derivative of the tangent vector to gamma d tau. Okay. By this I mean the horizontal direction. So I've drawn a picture as if gamma of tau is in this moving manifold cross time For this, I think of it just sitting in the manifold. There's a path in the manifold. It has a tangent vector in the manifold, and I measure the length with respect to the metric g t naught minus tau.
And time coordinate, what does it varies with speed 1, right?
Yes. Yes, that's what this says. Speed minus 1, shall we say.
Okay.
Yeah. Right. So this is a strange, this is a scalar curvature at that point under the appropriate metric. So this is a strange functional as far as I'm concerned. First of all, it has this funny square root of tau out front, but we call it a length, and indeed it behaves like a length, but this looks more like an energy. So I'm not sure. I mean, he has explanations of how he came up with this. They didn't convince me that this was natural, but it certainly works. So this.
What if you put a coefficient in front of like second term? Will it be as good as the?
No. Many of the computations are quite delicate, and use the coefficient. No. So this.
Not even 3.
No.
Dimension.
Oh well. No, I don't think so. I think these computations don't see the dimension really. This now scales like the square root of time, so it scales like distance. So that's why it's natural to call it a length, even though it has this funny thing in there. Somehow it's compensated for. I don't know. And the natural thing to look at is the scale invariant quantity. Okay. You minimize that over all paths from here to there, and you call that, so L min of yt. And this is the local version of entropy. And what it's used for, so when you want, all these arguments in Ricci flow proceed by taking geometric limits. You're trying to prove something exists for a sufficiently large time or for a sufficiently large constant. You suppose there is no time or constant, and you take a sequence of counterexamples with larger and larger time or constant, and you try to extract a limit and get a contradiction. That limit has to be a geometric limit. Now, when you go to take geometric limits of manifolds, that really means C infinity limits. You have to control two things. You have to control the curvature and all its covariant derivatives, and you have to control the injectivity radius at the central point around which you're working. Because if you can control the curvature and all its derivatives, that says the Gauss map is nice, out until it starts hitting itself. Well, that's the injectivity radius. So if you've bounded the injectivity radius away from 0 and you've bounded the curvature and all its derivatives in the Gaussian coordinates around that point out to a certain distance, you have complete control. And then by the Scalia, whatever it is, theorem, you can take a limit. Okay? Now we have a parabolic equation. As long as you flow for a certain amount of time, once you control the curvature, you get control on all the derivatives, because of the parabolic nature of the equation. So really we only have to control two things. We have to control the curvature, the Riemannian curvature, just its norm, and we have to control the injectivity radius. This is the technique that controls the injectivity radius. This is it. So it's some sort of entropy that's then turned into a control of size of small balls with the injectivity radius. And that's one of the two things, basic ingredients you need in order to take these limits and prove all these kind of geometric statements by contradiction. And it is a local version, and it behaves well past surgeries because you prove that anything that comes near one of these surgeries has a huge length and therefore is much bigger than the minimum, so you can again apply maximum principles to see how this function behaves at its minimum and so on. So this is a local version of that entropy functional. And in fact, somehow, I haven't ever worked out the details, the entropy functional can be gotten by integrating this local function.
So you call L little the local entropy, and what about the big letter?
The W? Oh, this is just, I mean, this is simply a step on the way to L. L is the important quantity. So this is called, Perlman calls this the L length. And he calls this the reduced length, I believe.
No, I mean only the small value makes sense, right?
Well, what you're integrating is you're integrating in a region down here, you'll be integrating e to the minus L d volume. And you want to make sure that's not too small. So you need this not to be too big. Yeah.
It's like a path integral or some statistical.
Well, you tell me. I don't know. I don't know what it is.
It has a definition, so it's not passing.
Yeah, I mean, this is certainly not a path integral, but it's. Yeah. Yeah, I mean, it's a class. I mean, you know, we're going to the minimum. We're going to the classical limit. Yeah.
Could you say something? Why this decomposition is finite actually? Is it a kind of a byproduct of what's written on the lower backboard?
I'm sorry.
Well, if we just run a flow and
Yeah.
face with a singularity, then we should somehow guarantee that there is only a finite number of them.
Ah, okay.
Just do you correctly.
So this theorem was proved without proving that there are only finitely many singularities. You can show, it's not too hard, that the singularities are discrete in time. So before a certain time, there are only finitely many, and that's enough, it turns out.
Because it can't happen that they accumulate. Yeah.
No, they cannot accumulate. And up until recently, it was thought, well, okay, maybe they're infinitely many. They won't happen out here because we're really getting hyperbolic convergence out here, but maybe they're happening in here. But just recently, a young postdoc, Richard Baumler, proved that there are only finitely many surgeries. So that's now a theorem. It uses the full structure of this argument. It uses everything. So it's not a direct proof there are only finitely many. It's an a posteriori proof that there are only finitely many. But that's now a theorem.
Is there a way to start Ricci flow from singular metric? I mean, you start from like something like polyhedron, right? You can try to smoothen it in a canonical way. Or maybe is there some canonical way to go through singularity?
Well, that's an interesting question. One could hope, I mean, the way I describe surgery and the way it's done, I guess the picture's gone now, I had to make choices. I had some singularities occurring in the middle of the tube. I had to go out toward the ends and decide what I was going to chop off and then exactly what I was going to fill in. I had to make by hand. You could imagine trying to go closer and closer to the singularities and prove some sort of convergence theorem and then have a weak solution through the singularities.
Some simpler forms of singularity, like conical singularities or something like this. Is there a way to canonically smooth them?
No, that's probably too much to hope for. What you might hope for is a weak solution through singularities. That you often have in these kind of equations. So you have something smooth, the equation develops a singularity, but nevertheless there is a weak solution through the singularity.
In some sense.
Yeah, well, it satisfies some minimization property. Unfortunately, we don't have a quantity here to minimize, so it's not clear how you would do that. You might hope that you can take limits of these surgery processes and show they converge, and thus there is some sort of canonical flow through the singularity that changes the topological type, but no one's been able to do that so far. But I think that would be very interesting if you could.
Mr. Wright, can you please repeat that is the argument you said which makes the point-correct conjecture a simple derivation from the first one?
Yeah. So first remark is it suffices to prove the Poincare conjecture for prime 3 manifolds. Because every manifold uniquely decomposes into prime pieces. If the manifold is a homotopy sphere, then all its prime pieces are homotopy spheres, and conversely. So I only need to prove the Poincare conjecture for prime 3 manifolds. Thurston's geometrization applies to prime manifolds. So it applies to this homotopy sphere. So there's a collection of tori in the manifold whose fundamental groups inject, and they decompose the manifold somehow. Well, there aren't any tori in this manifold whose fundamental groups inject, because the fundamental group of the manifold is trivial, and the fundamental group of the torus is z cross z. So this decomposition is the trivial decomposition. So the manifold itself has a homogeneous metric. Now you go through the list, I haven't written it down, but you go through the list of all homogeneous three-dimensional geometries, and there's exactly one that has a compact universal cover. And that's SO4 mod SO3. So you have to go through the list, but.
I'm sorry, can you repeat the last sentence?
Yeah, so I now have this manifold that has a homogeneous geometry. So I want to, it's simply connected and so it's got a locally homogeneous geometry, but in fact it has a homogeneous geometry because it's simply connected. It is its own universal cover. So it's G mod H. A Lie group mod a compact subgroup.
Now you say it is a sphere.
Now I say you look at the three-dimensional possibilities, and the only one that could be a 3-sphere is SO4 mod SO3.